Aloha and welcome to week 2 of Science and the Sea. Our first lecture this week is all about Earth's internal layers. So the Earth is not solid all the way through. The layers differ by composition, by density, and they are what actually causes those tectonic plates to move. So we're going to talk about all of the Earth's composition, its density, and its temperature today, and how those differences make our planet what it is. They're what causes volcanoes and earthquakes, ocean basins to form, and all of that movement is caused by these different layers, their densities, and their temperatures within the Earth. So you can almost think about the Earth as like a layered fruit, the crust being the skin, the mantle being like the part that you eat, like the thick, juicy flesh, and then the core being like a dense seed. So think of it that way, and we are going to look at all of those layers. So the structure of the Earth, we have the crust, the mantle, and the core. It sounds easy, but it does get a little more complicated than that. So the crust is thinner in general than any of the other layers. We have two types of crust. We have oceanic crust, which is where oceans and water are, and we have continental crust, which is where land masses are. So the differences are that oceanic crust is generally denser. The water is really heavy that sits on top of oceanic crust and makes it really dense. Continental crust is generally less dense and more often made of granite. The mantle is below the crust and it is a thick semi-solid layer of mostly, some of it, the upper part is liquid, the lower part is more plasticky almost. We talk about it as being a plastic-like layer. And it goes to about 2,900 kilometers deep into toward the center of the Earth. And then the core we have both an inner core and an outer core. The outer core is mostly made up of liquid iron and nickel. So for iron and nickel to be liquid, it has to be super, super hot in the core. And then the inner layer is essentially solid iron and under a lot of pressure. So the heat that's within those layers of the Earth is actually what drives the mantle to move and what drives our continents to move over time. So kind of interesting and a little dense. Okay, here's a diagram to kind of show what this looks like. We have crust on top. The asthenosphere, we haven't talked about too much yet, but the asthenosphere is the layer of the mantle that is molten and liquid and moving. And so the crust and the tectonic plates essentially float around on top of the asthenosphere. So the asthenosphere is just that uppermost layer. Then we have the more solid mantle, the plasticky type layer, and we have outer core and inner core. And you can always come back to this image to help you out anytime you need. So density and composition. The density and therefore the composition is really what drives the motion within the plates and within the center of the Earth. So the layers are arranged by density. Heavy materials sink, lighter ones rise. That is going to be a theme throughout our entire semester. Knowing a little bit about density will be super helpful for you, and know that always heavier materials sink and lighter ones rise. So this process is called differentiation, when heavier materials sink and lighter ones rise, and it explains why ocean crust, which is more dense, is lower than the continents. So we always have continents above and oceans below, and this is why, because those continental crust pieces are lighter. They're less dense than the ocean parts to it. So you can think of Hawaii as an example. The Pacific Basin exists because that dense crust spread out and sank as it cooled, creating more space for water to gather in that basin. So remember, density determines the structure, and structure determines how Earth behaves. All right, now we obviously saw that it's hot in there, but why? How did it get hot? There are two main sources. One is the heat that's left over from the Earth forming 4.5 billion years ago. So there's just still residual heat from that formation. The second is radioactive decay. There's uranium, potassium, different radioactive isotopes within the mantle and the crust. And as those decay, they produce heat. So heat comes from those two sources mainly. And that is what drives the mantle to move. So that's what drives convection currents, and that's what makes those plates slide around and move on the asthenosphere. So you could almost think of it like heating soup or something up on your stove. The more warm it gets at the bottom, then it rises toward the top because it's while the cooler stuff sinks, and that creates circulation. And that's similar to what's happening in the world. That's what fuels volcanoes, earthquakes, seafloor spreading. We can think about the Hawaiian hotspot, which we'll talk about a lot more later, but it's an especially hot upwelling of mantle material that comes up through the surface and forms our islands. So without that heat engine, Earth would be essentially have no movement, be essentially geologically dead. Nothing would change. No new crust, no ocean trenches, no volcanic islands. So it's actually a good thing that the center of the Earth is really hot. All right, moving on to the lithosphere and the asthenosphere. The lithosphere is the rigid outer layer, so the crust and the upper mantle of the Earth. So that's the part that's hard, essentially. The asthenosphere is what is partially molten and plasticky. That's what I keep calling that plastic layer. It's what floats, or it's the liquid that the lithosphere floats on. So the lithosphere is the crust and the very, very top layer of mantle that's solid. Those layers then float on the asthenosphere, which is essentially molten and flexible beneath, and it floats around. It's what moves, and those things float on top of it. So essentially the plates float and move on top of the asthenosphere. So if the Pacific plate keeps moving to the northwest like it is, what might happen to the Big Island in a few million years? I mean, obviously none of us will be around to see it, but it could happen. So think about that for just a second. The answer is that Hawaii will eventually move off of the hot spot in the Earth where it's at, and a new island would form to the southeast, and we here on Hawaii would no longer have any active volcanoes. Here is another image just to kind of bring home the different layers and how they work. So we have up top, we have crust. Here we have oceanic crust. Here we have continental crust, and each of them are listed. We have the lithosphere, which is the crust and this layer of mantle that's essentially solid. And right below that, we have the asthenosphere, which is the more liquidy layer. And sometimes we'll get a subduction zone where that crust is pushed down. We'll talk about those later, but for now you don't have to worry about it. We'll talk about that in lectures 2 and 3 of week 2. So the magnetic core, the magnetic field and core of our Earth. So that liquid outer core, the motion of it is what generates Earth's magnetic field. So that liquid outer core moves as our planet spins, as our planet rotates, and that generates electric currents that create the magnetic field of our Earth. That magnetic field actually shields our planet from solar radiation. If we didn't have that magnetic field, we as humans certainly couldn't survive, and most life on Earth wouldn't be able to survive because we would be radiated very quickly. So super important, really a big deal. The magnetic field has actually reversed a few times in history. So essentially the North Pole and the South Pole have flipped different times in history. The last magnetic reversal is thought to have occurred about 780,000 years ago. So it's not something that happens very often, but it's essentially like a giant magnet that occasionally flips upside down, which is, again, a little bit weird and a little interesting. So Earth's layers and ocean basins. Everything that we have learned so far connects directly to how Earth's ocean basins are formed. So that layered structure helps to explain how seafloor spreading happens, how volcanoes occur, and how those ocean basins form. And we're going to talk more about that in detail the rest of the week. But for now, just know that that's caused by the layers of the Earth, and that some of them are molten and tend to make holes and pop up through. The mantle convection is what causes the link between Earth's interior and the ocean floor. So we can think about the Mariana Trench, the deepest place on Earth. It formed when the Pacific Plate subducted underneath the Philippine Plate. And again, we'll look at that later. We'll look at that in week 3. We'll talk about all of this a little bit more. But really, all of this movement is going to become really important here soon. So a few things to think about. How does Earth's interior shape the ocean we see today? Where do you see evidence of this around our island? Volcanoes, earthquakes, hot springs. We have all of those here on this island, which I think is pretty amazing to get to see. But now you're starting to understand where these things come from and why we have them. So we talked about Earth's layers, how they are dynamic. They don't stay the same, they change. And the internal heat within the mantle and the core is what drives convection and causes that motion. And the motion is what shapes the ocean basins that we see today and that we are studying in our entire course. So as always, sources are going to be on Lamaku. And next, we will be talking about continental drift and plate tectonics. So we're going to get a little bit more into the history of continental drift and talk even more about plate tectonics next.